My name is Cem Zeytinoğlu, and I'm a professor of communication at ESU here. I also serve as the co-chair for the committee that puts together this a great event. So welcome to the Provost Colloquium series. Tonight we are going to have Dr. James Hunt from the biology department. So I would like to welcome everyone for this significant event. Again, thank you for your support. In order to introduce our lecturer today, our presenter today, I'm going to invite Dr. Peter Hawkes, the Dean of the Science and the Arts.
Thank you. Thank you, Cem. The provost who started this colloquium can't be here tonight. She sends her apologies that she's not able to. So I'm honored here today to introduce Professor Jay Hunt's lecture on exploring the effects of climate change on our oceans. Now, studies tell us students are not adequately prepared for careers in science, engineering, and mathematics. Yet our nation's future depends upon excellence in these areas. We face a number of crises that only scientists can address. Ozone layer depletion, our over-dependence on fossil fuels, and our growing carbon footprint on this tiny green planet. Climate change, weather changes resulting in terrible droughts and terrible floods. ESU believes an investment in scientific research will yield enormous benefits for our society. So we have tremendous faith in our scientists here. We have faith in the research they do, and we have faith in you, the students, who are here to be educated in science and who will go on to benefit our society. Dr. Jay Hunt is a marine biologist in the biology department, and in his talk he'll make several points. One is the issue of climate change is complex, but the scientific evidence for climate change is unambiguous. Number two, while the scientific evidence is clear, one area of uncertainty is the role oceans will play in regulating or mitigating climate change. And third, he wants to shed some light on ESU students who have engaged in research to better understand how climate change affects our oceans. So let's give a warm welcome for Dr. Jay Hunt.
Thank you very much. I want to thank the provost and the committee and the dean for inviting me to come and speak today. It's an honor to be here. I appreciate everybody that turned out. I'm giving a special shout out to my students who have heard me talk about climate change once or twice or 3 times or 4 times before. But I'm absolutely glad that everybody has a chance to come tonight. I'll tell you the honest truth. A couple of weeks ago, I went to Dr. Connolly and Dr. Kitchens-Kin's talk, and it scared the bejesus out of me because it was so good. And I thought, well, great, how am I going to follow that act? And I came away thinking, you know, I just really feel like I enjoyed that hour and I got something out of it. So that's my number one goal today, is just when you leave here, hopefully, you'll feel like the time was well spent and maybe you got something out of it. So that's my main target. I will say that I've been interested in climate change my whole career. I started as a geologist. My undergraduate degree is in earth science, and switched to biology in graduate school. It's something that I've been studying for almost 30 years, and so I'm keenly interested in it and discussing it, and I hope that that will come across as well. I've kind of divided things up into 3 parts, and after each part, I'll stop and I'll see if there's any questions that you have or discussion points you want to make, or tell me I'm wrong, or whatever it is that you want to do, and so we can have that discussion. Really up to you. So, first, I need everybody to play along. Even if you don't think you know, You have a gut feeling, pick a side. I want to see everybody's hands go up one way or the other, true or false. Global average temperatures declined from the mid-1940s to the mid-1970s, even though CO2 went up. How many say that's true? Put your hands way up so I can get a sense. How many people say that's false? Yeah, I'm going to argue that's true. I'm going to argue that's absolutely true. I'm going to show you some data in a minute. True or false? In 2015, NASA scientists reported that ice in Antarctica had been increasing since the last ice age and is continuing to increase today. True? False? About half and half. I'm going to go true with that one too. I'm going to say that one's true, and we'll talk about all these in just a minute. My students are laughing because I start my talks like this. We've all heard the Greenland ice sheet is melting, right? That freshwater ice sheet on Greenland is melting. True or false, the actual sea level near Greenland on average has been dropping, continues to drop. And the second part, these both have to be true for true. NASA says the global average sea level has been dropping since about late 2015. True? Probably about a quarter. False. Yeah, that one's true too. So, how many people are getting a little nervous? Like maybe this isn't what you expected it was going to be? It probably is what you expected it was going to be. It is going to be. However, I bring these up for a point, which is it is a complicated issue. Climate change discussion around climate change is very complex. And one of the things that I try to teach the students is if you're going to take a position, you have to know evidence, you have to know data, you have to know arguments. Otherwise, you're going to get caught arguing a point that isn't true. I also will point out to you that it is important in these sorts of discussions, I think, especially with the way people tend to argue and get into political debates, that for some of you, you probably noticed you had like a pit forming in your stomach, maybe a little tightness in your throat. You're getting a little angry. That's because human beings aren't really good at distinguishing physical threats from threats to our ideas. I think that's probably the most important thing in trying to have a rational discussion about climate change than anything else, is to recognize you have this visceral response. And if you recognize that about yourself, try to keep that in check as you listen to evidence and try to have an open mind about it. Now, for people that might start to feel amused and comfortable, if you're going to accept those truths, here's some other truths for you. Global average temperature has risen about 1.4 degrees Fahrenheit since 1880. 2/3 of this warming has occurred since about 1975. The warming rate has actually accelerated from about 0.07 degrees per decade in the 20th century, 2.5 times that rate to about 0.18 degrees Celsius per decade now. The Arctic is currently losing ice at a more than double rate than the Antarctic is gaining it, and that study in 2015 is highly controversial. If you're going to look for scientific debate, there is debate about what's happening in Antarctica right now. And when I say NASA scientists, it was one group of scientists who released a report based on satellite data, and there have been scientists that say that isn't quite accurate. Even if it is, we're losing ice in the Arctic at more than twice the rate. And since 1880, global average sea level has risen by about 20 centimeters, although there have been years of decline. And about half of that rise has come since 1993. So I point out to you in all of this that not only do these facts also look and sound and ring true and have evidence to back them up, but the highlighted parts show that in most cases the change is accelerating, not stabilizing, slowing down, reversing, but actually speeding up. So how does this then tie into what's going on today? We've had some interesting headlines in recent days. I was sitting in my office on Friday when the news broke that our fourth climate assessment report was put out by the Trump White House. And I had a reaction that many people interested in environment and climate had, which was, huh? I was surprised. I really was. I thought maybe somebody was sleeping. I'm not sure exactly, because the report is pretty clear and unequivocal about the evidence. We also had the COP23 beginning in Bonn. I think it was yesterday or the day before. And the news last night broke, of course, that with the joining of Syria to the Paris Accord, the United States is now the sole nation on the planet that's not part of the Paris Agreement. Why do I start all this way? Because, as I said, as a scientist, we can look at data and we know that the data actually promised myself when I first started I wasn't going to use a lot of graphics, and I just decided I can't, because why should anybody believe me without data? So I will tell you that this data comes from the NASA Goddard Flight Facility. It's pretty much a standardized data set that's used in this kind of discussion. And the black marks the annual mean temperatures. The 0 point is the average between 1950 and 1980. The red bar is a 5-year average mean. And if you look at that data, you could draw a line that shows a decline in temperature. I mean, let's be honest. And in fact, if I look from 1998, when we had a huge El Nino, maybe you could draw a slightly declining line, although I have to say since 2014, 15, and 16 were the hottest 3 years on record in order, the first trifecta we've had, so to speak, since 1880, that I think once those data are in, even this bit of data is not going to hold up. You don't really talk about 1900 and 1910, although that's actually, for the 5-year average, the most convincing decline in a decadal scale since the data go back. Probably you know what's going to come next here, which is I can look at all those 3 sets. The problem is when I fill in the rest of the data, right? So one of the issues becomes, in discussing things, we have to be honest about scale. We have to be honest about what we're talking about. And it is true that the temperature's been warmer in the past. We've had periods in Earth's history where there have been no ice at either pole. We've had periods in Earth's history we've had ice at the equator. That's not the point. The point here about climate change is the rapidity of change and how fast things are moving. So I think at the very least we should do is start out by thinking about how we're talking about data and trying to be at least a bit honest about what we're saying. Here's the data from NASA on sea level rise since 1993, starting at 0, set 0 at 1993. And you'll see up here from late 2015, yeah, it's gone down a little bit. Now, when I saw the climate skeptic websites about this, it was NASA released this report that shows sea level is falling and nobody wants to talk about it. It's true nobody wants to talk about it, probably because it also happened in 2013, 2011, and 1998. 3 of which, of those 4 events, coincide with the 3 biggest El Nino years we've had. NASA has 2 satellites called the Gracie satellites that found where the water went. So if the question is where does all this water go, it turns out it mostly goes into the Australian basin and northern Brazil, and based on the topography there, it takes about 18 months for it to wash back out to the ocean. The odd one is 2013. That one's a little weird. So again, if we're going to be honest, I don't quite know how to explain 2013, although people have tried. I don't think it's that convincing. But 3 out of 4 isn't bad. If we look then at the whole trend, here's a NASA data set looking at Arctic sea ice from about 1978 to 2016. You'll see it in millions of square kilometers going up and down, bouncing around quite a bit. down to 2012. This goes to 2016. Just to remind you, if I look at that whole trend, to me, it looks like it's going down. To remind you, this is kind of where we started. The estimates are about 30% of that cover is gone. Estimates are that without any acceleration, which we are pretty convinced is happening, that we will have ice-free summers at the North Pole by 2050. Many argue that's going to happen earlier, as early as 2040 or even 2035. So there's a prediction. You know, hang on to your hats for 20 years and see if the North Pole is ice-free during the summer. I will also point out in this sense of trying to get this debate, this discussion of these kinds of things happening, that I kid you not, as soon as that spike from 2012 went up, the news was the decline in sea ice is over in the Arctic. It's gone up 30% since 2012. That was the headlines in 2013, 2014. You can't just pick this little slice and pretend that suddenly now. You've got to do yourself a favor and look at the entire data set over a longer period of time. So the point of this is it's complicated. There was a scientific study that showed that sea levels falling around Greenland, even though the ice is melting. Icebergs are big. They have a lot of mass. We know that that's going to create gravitational attraction. That's what mass does, meaning that iceberg pulled the water towards Greenland. When the ice melts, the gravitational loss is there. The same study, of course, goes on to say that the overall sea level from that melting has risen. But right around Greenland, it drops for different reasons. Complicated, right? If you're not paying attention to details, though, that's the kind of stuff that makes everybody's eyes glaze over. Well, one scientist says this, the other scientist says that. They don't know. They're contradicting each other. They're not. At the same time, as a scientist, you can't ignore data. You can't ignore studies because they're inconvenient and don't fit in to your narrative. You have to be able to explain what these studies are saying and put them in context. So when I talk about these kinds of things with students, I try to go to what can we know with reasonable assurity? What are the kinds of things that we can say with pretty high confidence that are hard to argue? And I'm going to talk about three things, although we just said it was complicated, and I'm going to try and simplify it. The idea of simplifying is not this is a slam dunk argument, case over. The argument is these are the three principles I'm going to start with. And if you're going to take a study out of context, I'm going to go back to, are any of these three wrong? One is CO2 is increasing. Two is CO2 blocks some of the infrared radiation causing more warming in the lower atmosphere. We call it the greenhouse effect. Number three, the CO2 increase today is coming largely from the burning of fossil fuels. This, I suspect, is the one that's more controversial today. 30 years ago, people argued about the CO2 data set. That one's kind of put to bed. It's very rare now to find somebody arguing with that. We have evidence, not just theory, that the greenhouse effect is real, so it really is starting to come down to this anthropogenic climate change caused by humans. So let's just look. Charles David Keeling, who was from Pennsylvania, yay, as a grad student in California, was famous for trying to figure out what carbon dioxide was in the air. The idea of the greenhouse effect predates him 60 years. It's over 100 years we've understood that this Earth's temperature should be a lot cooler than it is based on its distance from the sun, but the atmosphere keeps it warmer somehow. CO2 is a likely candidate. The problem is everywhere he went to measure CO2, it was too close to the street, too close to traffic, too close to this or that. So he settled on the Mauna Loa Observatory in Hawaii, and in 1958 started recording CO2 data. It's still there today. This is the main CO2 tower. It's 27 meters from top to bottom. It's taking air in from the top and the bottom, calibrating to make sure there are no differences. It is calibrated with three standards of carbon dioxide every hour and takes measurements every day. It's a pretty convincing data set. It's not the only one. There are now over 120 data sets like this in 66 different countries that all say the same thing. So if this one's wrong, the other 119 also have to be proven wrong, and they're all wrong in the same way. That's pretty unlikely. So if one's wrong, and this one's wrong, and that one's wrong, if they're all wrong together. That seems highly suspicious if that's true. So we've got CO2 going from about 315 parts per million back in 1958. Last year went over 400 permanently, because even the low time is at 400. The bouncing up and down has to do with in the northern hemisphere in the spring, trees put leaves on. That's more CO2 drawdown for photosynthesis. They shed their leaves in the fall. CO2 goes up annually. So you get this annual bounce. But the overall trend is pretty clear. So CO2 we know is going up based on that, plus all these other data sets that all concur. Next we come to the greenhouse effect. And I try to keep this simple and try to explain it quickly. If there's more questions about it, we can talk about it. But the basic idea is that sunlight comes in at a certain spectrum that's in the visible light. And the visible light spectrum, the frequencies don't interfere much with any of the gases in our atmosphere. And about half of that energy is reflected back or stays in the atmosphere. About half gets to the earth, where it warms up the earth, warms up the waters, warms up the earth. The earth, in turn, radiates its own energy at a much lower temperature. Earth is a lot less hot than the sun, and that temperature happens to be mostly in the infrared spectrum, which our eyes aren't attuned to see. The infrared bumps into some molecules and not others. And the molecules it bumps into are the greenhouse gases, CO2, nitrous oxide, water vapor, ozone, those sorts of things. The idea then is if you put more of these greenhouse gases in the environment, they're going to have more interference with the IR spectrum, and then that is going to cause an increase in IR energy to stay near the surface. Nice idea. Is it true? Yes. It's not just theory. There's empirical evidence, pretty convincing empirical evidence that this is true. How? Every molecule has a unique fingerprint, if you will, of the different spectra that it will absorb. Between 1971 and 1996, satellites measured a decrease in those spectra where CO2 and nitrous oxide, methane, et cetera, should be absorbing them. More than that, after these energies are absorbed, the molecules re-release again in the infrared spectrum, but slightly shifted, slightly different wavelengths in all directions. Up, some will eventually go to space, sideways in the atmosphere, but some of it is pointed back down. You should see then an increase in those frequencies on Earth, and we do. And they match the intensity, and they match the frequency spectrum expected. To me, that's empirical evidence that the greenhouse effect is not just an idea. We've measured its trapping heat. Why humans? There are a lot of different arguments that can be made for why this is an anthropogenic effect. And we can talk about any of these. As a scientist, when one line of evidence points you in a direction, you think, that's interesting. When two, it's curious. When 3, 4, 8, now it's starting to get a little overwhelming. If something is going to make this idea fall, it's got to make it all fall. But I'm only going to focus on one, because I feel like this is the most convincing one for me personally. Maybe it will be convincing for you. The carbon fingerprint that we have in our atmosphere, we're pretty sure is coming from the burning of fossil fuels primarily. And here's why. If we look at, there's 3 types of carbon in the atmosphere. Carbon-12 makes up the vast majority of carbon, 99%. Carbon-13, which is a little heavier, makes up about 1%. and I know that adds up to 100%, but about 1 in a billion atoms of C is C14. C14 is primarily made in the atmosphere through solar radiation. And when animals ingest C14 and then they die, the C14 over time decays. This is where carbon dating comes from. The half-life decay rate is about 5,700 years, which means that if I die tomorrow, the bones that have C14 in them, half of it should be gone in about 5,700 years, half of that in another 5,700 years, half of that in another 5,700 years. That's not that long in terms of how long it takes decaying plant matter, for example, to become fossil fuel. In 500,000 years, it's effectively gone. That's why you also can't carbon-14 things that are much older than, I forget what it is. Anybody know 100,000 years, 150,000 years? It's not very useful beyond that because it's just not sensitive enough. Carbon-14's gone. So if you then burn fossil fuels, they should be carbon-14 clean. And you should see a decrease in the C14 ratios in our atmosphere, which you do. And the C14 decrease corresponds pretty well with the amount you would expect if you're burning fossil fuels, with one exception. The late 40s and 50s, when we did a lot of atomic testing, and we put a lot of C14 in the atmosphere, and we kind of screwed up the data set. So you don't hear too much about C14 anymore. But I think you will again, because the data is getting clean again, and we're seeing the C14 going down again. But we still have C13. It turns out that most plants, when they do photosynthesis, prefer to use C12 over C13 in their carbon dioxide. Not much, about 2% on average. But it means those plants that are making fossil fuels over millions of years have less C13 in them when you burn them. So if the CO2 increase is coming from fossil fuels, you would expect the C13 ratio to also drop. And it does, and it has. And it's demonstrable in several ways. Tree rings, pore water, direct atmospheric measurements, coral skeletons, all of them have declining C13 rates. All of them correspond more or less with increases in CO2. This graphic here on the right, the negatives are actually going up to kind of show you it's kind of flipped on its head. But the black line is anthropogenic CO2 output. The red line is what the C13 ratios are doing. It's not perfect, but it's fairly convincing. Add it to the fact that nights are warming up faster than days, which is what you would expect under climate change. Add it to the fact that the carbon budgets don't make sense any other way other than looking at anthropogenic sources. Add it to several other facts that I showed you in the last diagram, and this is why most reasonable scientists believe this is from human sources. How much? Couldn't tell you. 97% consensus? No. It's not 97% of scientists. It was 97% of climate researchers. That I agree with. But if you take that and say there's this vast consensus among scientists, again, you're kind of mixing up information. What's a scientist? I'm a scientist. I wasn't part of that 97%, even though I believe it. So the original report talked about a consensus among climate researchers. That was about 97%. It has since been attacked. It has since been done 7 different times, and the numbers all come up between, I think, 91% was the lowest and 98% was the highest. So the people that are producing the most work in the area are pretty overwhelmingly convinced that it's due to human changes. So that's my primer on climate change. CO2 we've measured is rising. We've measured the greenhouse effect is real and is trapping heat. And we know because of other things, but in addition to C13 ratios, that it is likely coming from fossil fuels. The question becomes, if that data is all convincing, what other argument could there be? So that's where I'll stop and ask for the first part if there's questions or comments or disagreements.
CO2 source, have they checked the oceans to see if there's any CO2 coming out of there?
So the CO2 is actually now going into the ocean.
Okay.
CO2 is taking up, I think it's 7 or 8 million metric tons of CO2 per year. And here again, I just told you, oceans are taking up CO2. I can find you 8 papers on Google in 2 minutes that say CO2 is coming out of the ocean, because it is at the equator where it's warm. But it's balanced out plus in cooler oceans in the temperate and polar areas. So on whole, the oceans are taking it in. In certain locations, it's coming out. So CO2 should actually be going into the ocean, and it is. About 25% of it is actually going in the ocean today. CO2 is going into biomass on land, plants. All of that stuff actually should be having a CO2 drawdown of, I forget the exact numbers, 15, 16 tons, million tons per year. But we put about 30 million metric tons per year into the environment, which is where you're getting that carbon budget from. And the amount it's going up is that excess balance. It's like your bank account. I start with $1,000. If I draw out 2 but put in 3, it's going to go up 1. I know where that's coming from. So yes, the amount of CO2 humans are producing is minuscule compared to nature. But that's not the point. Nature has and always will shed off carbon and take it up. We've changed that balance to the point where instead of taking up some CO2 now, we're accumulating CO2 at the time.
Let somebody else answer. I got another question.
You're the only other one.
Okay. How much has development impacted the uptake of CO2 on land? I mean, we are putting CO2 out there, but now we're also cutting down all our trees, covering our
Yep.
plants.
So this is off the top of my head, best of my recollection, about 9%
Okay.
of the total CO2 sinks come from land use and development and things of that nature.
Just curious.
Do you think that since it's such a norm, quote unquote, to have a vehicle, do you think that's also kind of helping in the greenhouse effect?
Say it again.
Do you think that since it's such a norm, quote unquote, that like everyone has a vehicle, that it's putting in a lot more carbon?
I mean, there's a lot of sources of CO2. Certainly, automobiles are one. But there's other sources, and it's not just CO2. Remember, there's methane, there's nitrous oxide, there's all those sorts of things as well. But yeah, we understand that one of the problems is the CO2 burning. So one of the other things I'll say to people is, we know when you combust materials that CO2 is released. It has to go somewhere, right? It's not escaping to space. So it's either going to go in the air, the land, or the water. And that CO2 is coming from different sources, natural and human-made. And human-made is a small part of it. But again, like that $3, $2 example, it doesn't matter that it's small. It's the balance that matters.
Does the heat coming from the sun, is it constant or does it vary?
Actually, right now and in recent decades, if it's the sun, it should be cooling a little bit. Some people say it's nothing, some people say a little cooling. The other issues with the sun, for example, the upper stratosphere is actually cooling. If the sun was doing it, you would expect that to be warming. Also, you would not expect daytime to be getting less warm or nighttime to be warming up faster. It should be coming from the heat of the sun. That's the opposite of what we see. So nobody's saying the sun doesn't have a role. It obviously does. What they're saying is you can calculate what that role is, that forcing, and it doesn't account for the change. Okay, so let me do part 2 here. This is the one that I was really surprised by. In the 1970s, it sort of became apparent that we didn't know enough about how much heat was going into the ocean, which is a big problem if you're trying to model climate and trying to look at this kind of information. Everybody knows that water absorbs more heat than air. It's got a higher heat capacity, the capacity to soak up some of the heat. So people started to try to find technology and put buoys around that would measure the heat in the 1970s and 80s, and there was a lot of engineering that went into it. And as late as 1995, with the little bit of information we had, the estimates were about 25 to 75% of the heat from the greenhouse effect had already gone in the ocean. Now that's a big unknown. And if you're trying to model climates, that's a huge unknown. Water vapor is a stronger greenhouse gas than CO2 is. Warmer waters, more water vapor, that's all going to matter. So in 2000, the Argo buoy program was established, array of real-time geostrophic observatory. It's over 3,000 buoys floating around the ocean, everywhere in the oceans, north, south, east, west, about once an hour relating temperature data back. And last year, you'll notice the data on this report is September 2016. That's only a year ago. The first decent study on what's happening to our oceans in terms of heat. So, is it going to be closer to 25% or 75%? Who thinks closer to 25%? 75%. Some people are not playing. This is what I woke up to one morning as I start looking through this stuff. Yeah. 93% of the heat that's been created since 1970 has already gone into the oceans, based on our best science. That's the graphic and what it looks like. The red is the atmosphere. This is where heat has gone. The green is the land. The gray is ice. The dark and light blue are the ocean. Dark blue being deep, which, by the way, is not really that deep. 700 to 2,000 meters. That's as deep as the Argo buoys are going reliably nowadays. Average depth of the oceans is closer to 4,000 meters, so this is not even half of that. But 93%, those dotted arrows are the 90% confidence limits, which means it might not be 93, it might be 88. It also might be 96. But somewhere in there is a lot of heat that's gone into the ocean. So the researchers went out and said, okay, if we took that heat that's already been absorbed by the ocean and we put it into the air. Now this is ridiculous. This can't happen. We know that. Water's going to hold on to that heat. But the point is, we want an idea of what does that heat mean. 93% is a lot. What does it mean? We're so focused on the atmosphere. What if that amount of calories, what if that amount of heat went into the atmosphere? Air temperature would have risen 36 degrees Celsius. I did not intend to write 3.6. So while we're arguing about 1.5 degree or 2 degree, the amount of heat that went into our ocean since 1970 would have risen air temperature by about 97 degrees Fahrenheit. So we should all thank the ocean, right? This is one of the key points that I wanted to make because I think September 2016, our focus was elsewhere, right? We had an election 6 weeks away or so. So this, how many people heard about this other than my students? Right. So I think this is a really big report and a really big deal, but it largely went ignored. And one of the key things here is we know the oceans are going to keep absorbing some of the heat. We're not sure for how long. We're not sure how much. Paleo evidence suggests there's about an 800-year lag before the ocean starts giving up that heat. But we really don't know because this is something unusual. We've never had a situation where the heat's changed this fast. So we don't know. And one of the lead authors of the report, P.C. Reed, says this right in the summary: by absorbing a disproportionate amount of heat from global warming, by taking up rapidly increasing emissions of carbon dioxide, the ocean has shielded the world from even more rapid changes in climate. However, the extent to which it can continue to do so in the near or distant future is far from clear. We don't know how much longer the oceans will do this. And by the way, they've also taken up about 25 or 26% of the carbon dioxide. We'll get to that in a minute. Oxygen. Why else should we care about the ocean? Every 2 breaths you take, one of them comes from ocean phytoplankton. So there, Amazon rainforest. Land plants make about 25% of the oxygen globally. Marine and freshwater algae make about 25%. About 50% come from oceanic phytoplankton. Just one species, Prochlorococcus marinus, cyanobacterium, 5 to 15% of the world's oxygen comes from this one marine bacterium that's a photosynthesizer. Who cares? We didn't know about it 32 years ago. We've only known about it for 3 decades. It was only discovered in 1986. We still don't know much about it. That's why it's 5 or 15%. We don't know if it's 5, we don't know if it's 15. We don't even know how much oxygen is really producing. We sure as heck don't know how pH change is going to affect it, how temperature is going to affect it, the interaction with other microbes and how that's going to affect it. Sally Chisholm, who's the scientist who discovered this from MIT, said it best last year in an interview, it really doesn't matter. It really doesn't matter if the change is happening from human causes or natural causes. We need to understand the ecology of the Earth's systems regardless. We all were pretty much on board with climate is changing, whether or not you believe it's anthropogenic. It doesn't really matter if we don't understand what's happening, and we don't understand what's happening. So I would put that as a second point. Earlier this year, first good study on oxygen in the ocean coming out of Germany says there's been about a 2% drop from 1960 to 2010. And last Friday, part of that climate assessment report expects another 3.5% drop in oxygen. Oxygen should be going down as you're burning fossil fuels. You combust things with oxygen. That's why you have to have oxygen for a fire. We all know that. And we are seeing a mirror image of oxygen now starting to show up with CO2. Sea level rise. I'll go through this one a little quickly because I'm getting a little warm too. It's risen about 8 inches since 1880. The rate is accelerating. About half of that 8 inches has come since 1993. About a third of the rise is coming from thermal expansion. As the ocean is warming, it's expanding. About 2/3 of it, not quite 2/3 of it, is coming from the melting of glacial ice, freshwater ice. Current rates are around 3 millimeters a year, 1/8 of an inch. That sounds like nothing until you keep the acceleration idea going and compound that over years. And we have, with about 95% confidence, the best science we have says about 1.1 to 4.3 additional feet of sea level rise by 2100. pH, this is one that's kind of near and dear to my heart in terms of research. That 25% of CO2 that's being taken up by the ocean is turning into carbonic acid, which doesn't stay long around in the ocean. It kind of breaks up into bicarbonate and some other things, but it protonates, it sends protons in the ocean. It lowers the pH. It makes the oceans more acidic. The oceans currently have a pH of about 8.11. 50 years ago, that was 8.25. It doesn't sound like much, but it's a 30% increase in hydrogen ions. Another point here that I hear all the time, how can we talk about ocean acidification when the ocean's not acidic? Remember from basic science class, pH neutral is at 7. Anything above 7 is alkaline, basic. It is basic, but it's less basic than it was 50 years ago. So it's acidifying, it's becoming more acidic, but it's not below 7 yet. And maybe it never will be, who knows? CO2 and H2O make carbonic acid. The lower pH makes building calcium carbonate hard parts, shells, tubes, etc., more difficult for marine organisms. This is a partial list off the top of my head of animals that have a lot of them, if not all of them, making parts with shells and things with calcium carbonate. Corals, clams, mussels, scallops, oysters, sea stars, sand dollars, sea urchins, brittle stars, sea leaves, barnacle, snails, many worms, sponges, and phytoplankton, including coccolithophores and foraminiferans. It's not a small group. Not calcium carbonate producers, but animals that use calcium and chitin and other things in their carapace. Lobsters, shrimps, prawns, crabs, cuttlefish, bony fish, marine mammals. It's not calcium carbonate again, but this calcified salts become harder to put down for vertebrates as well. Thin calcium carbonate shelled swimming snails. This is an experiment done with different lowering of pH as expected under moderate climate scenarios to 2100. The upper left is what it should look like. It kind of becomes opaque at first when you lower a little bit. It starts to become pitted and hold until the shell actually starts to dissolve with a change of about 0.15 pH, lower than what current ocean conditions are. Coral cups, calcium carbonate. This is what a healthy one should look like, the upper left. Again, lowering the pH slightly to what we believe will happen by 2100. Coral cups are barely able to form. This brings me to coral reefs. Now stay with me for a minute. If you're not a biologist, this is, I promise, I'm going somewhere with this. Corals are little tiny animals that make calcium carbonate skeletons, make big reefs, calcium carbonate, biggest reef formers of our time. Going back before 50 million years ago, other things made reefs. Now it's corals. We already have, this is from NOAA data, National Oceanographic and Atmospheric Administration, in 2013, 27% of coral reefs since 1950 are gone. Best estimates are 55% more are either going to be gone or very close to gone, more than 70% damaged by 2050. All of these things are bad for coral. The acidifying water, I just talked about. Warming temperatures, corals like warm water, but not too warm. You get it above 82 degrees, they bleach, they don't like it. They like warm, not too warm. Increased pollution, sea level rise. The idea is if I'm struggling to make coral, make a skeleton to grow up and the sea level's rising, so on the top of me trying to work harder to do that, the sea level keeps getting higher and higher. All those things work against corals. In 1998, at the time, biggest El Nino event killed 16% of the corals worldwide. We have since had two larger El Nino events. El Nino, if you don't know, are these big heat shifts that happen in the equatorial Pacific that used to happen every 4 to 11 years. We know this from guano records of all things in Peru going back 400 years. They kept really good records of how much guano they were exporting. And you could see these spikes, or declines, I should say, in the guano production. So every, I say 4 to 11, 7 to 11 years. Now, the most recent ones are coming every 2 to 4 years. And they're bigger than we've ever seen them before. The most recent one was the biggest we've had, lasted for the longest period we've had, and made 90% of the Great Barrier Reef bleach, which means lose its symbiotic algae that it uses for sugar, for food. Now you can come back from bleaching if the conditions are okay. If things return to normal in like 4 to 6 months, you can become healthy again. That's not what's happened. So 90% of the reef has bleached, doesn't mean it's dead. But about 30 to 50%, we're not sure exactly where, in that range, died last year. It's the biggest reef system on our planet. Now, I try not to scare students. I try not to be that person, the sky is falling. I don't like that kind of thing. And I try to actually be as careful as I can about data. The 93% surprised me. So I was a little taken aback by that. I'm going to show you something in a minute that I, again, don't think gets enough attention. It's pretty easy to find these kinds of graphics now. We know when the El Ninos are coming. So you can set up cameras on time lapse and get these kinds of shots, the before healthy, the after bleaching. There's a shot of the Great Barrier Reef, December 2014, nice healthy staghorn coral, bleached but not yet dead. Dead. Algae comes in, takes over, it's not growing living tissue anymore. Upper left, what the coral should look like, nice and brown and healthy. Lower is what we see when we see these bleaching events. And we can actually see this from the air as well. should have nice green lagoonal waters with kind of brownish algae color of the corals. When it bleaches, you can see the white patches. So you can do an aerial survey to get the big picture, and then you do diving surveys to get the ground truthing. This is the one that I don't think gets enough attention. 2008, Vernon, who's a paleoecologist, did a pretty exhaustive study of all the major extinction events that have happened in the past. Now I'm just going to give you data. That's all I'm doing, is trying to tell you about a report that I think hasn't gotten enough attention. We've had 5 major extinction events. Some people would argue we're going through a 6th. I'm not going to make that argument. We've had 5 in the past. 4 of them came on the heels of the demise of the calcium reef builder of the day. Now is corals. At one point it was bivalves, reefs, clams. I mean, it's been different animals. But you'll see that the reef goes and then the extinction event happens. Could be a coincidence. It's a correlation. It's not causation. True. But interesting nonetheless, I think. The only one that didn't happen was the oldest one we have, which was the Ordovician. The dinosaurs went extinct. In this one here, the Cretaceous tertiary boundary, about 75% of species go extinct. End of the Permian, 95% of species that we knew about go extinct. In the ocean, it's even worse. It's 98.5% of marine species went extinct during this period. So yeah, things have always changed. True. I'm not going to argue things haven't changed. There have been times when the CO2 levels were 4%, not 0.04%, 100 times what they are today. And like I said, there have been times when the ice went all the way down to the equator. So I'm not sure I buy the change argument. It is unclear what animals might, or plants or organisms might be able to adapt to fast change in pH. The best evidence we have suggests that if there are things that can change fast enough, they're typically things like bacteria, maybe some protists, the non-calcifying kind, because the calcium carbonate's not going to be easy to make. There's been speculation that things like jellyfish might actually prefer an acidic ocean, so maybe they'll thrive and do well. Best evidence for this suggests that actually we're not seeing more jellyfish blooms right now. We're seeing an increase looking for them. So the rate that we're looking for them and finding them, it's hard to tweeze out how much of this is just on our radar screen. So part of the work that I'm trying to do is look at baseline data for these kinds of animals, because we can't say if it's changing if we don't know what's there to begin with. So that's kind of what we're talking about in our work, which is the third part. So let me stop at the second part and ask if there are questions or comments or.
The heat the ocean is absorbing, is that what's causing the majority of the ice to melt, or is it the air temperature that's also contributing a lot? I mean, what is the contrast between heat in the water and heat in the air?
So there's a really good question, and I'm going to give you my best guess answer, and this is based on kind of what I'm piecing together. I think most of it, people would agree now, is driven more by air circulation than water. However, the sea ice sheets, particularly in Antarctica, there's a big concern that water underneath them is warming. And there's a big unknown about how that might affect Antarctica. So whether or not ice is growing in Antarctica or not is a source of debate right now. What's clear is that sea ice is growing. That should make sense if the land ice is melting and going into the ocean, and then during the freezing time makes that water colder. It's easier for that water to freeze and expand. The water underneath it is warming as well. And it's an open question if that's accelerating or not. I think it is, but the evidence for that is not as clear. So it's probably a bit of both. Other thing? You guys wish there's some prochlorococcus in here right now, don't you?
Well, I got another question I was going to ask.
Yeah.
With the amount of, for the bacteria and algae that photosynthesize, is their carbon, are using their CO2 from the ocean, or are they getting their stuff from the air?
Most of it is bicarbonate.
Bicarbonate,
Right.
okay.
So when you make calcium carbonate in the ocean, typically you take 2 bicarbonates and a calcium. You make calcium carbonate and you actually release CO2.
Okay.
So
But what I'm saying is you got an increased amount of CO2 in the oceans through carbonate. Then should you also see an increase in these algae? Or is the
So-
pH sort of then kind of counteracting that effect?
So there's 2 different types of calcifiers. There's calcium makers that make what's called calcite, and ones that make aragonite. Those should both decrease if pH goes far enough. Aragonite first and calcite next. If the pH goes that far low, you should start seeing photosynthesizers, autotrophs that don't make calcium carbonate like it and increase. They should flourish because there's no
That's
reason
kind of
why
what
they
I was
should.
saying, yeah, okay, all right.
And there will definitely be, you can make cases, and people are making cases, that there should be some level of production increase in some locations in the world, and in other locations will probably not have or have losses. But there is an argument being put forward about how CO2 is going to change us all for the good. It's not an argument I'm willing to make, but it is out there. Haley.
Why is it that, if we know when El Niños are coming, why is it that nothing was done to try to help protect the Great Barrier Reef, or it's just because there's really
I
nothing?
think it's just too big, is my guess, right? It's just too big. Plus, this is a new one on me anyway. So between El Nino, there's usually La Nina, where the temperature has a certain change and goes down. It didn't go down enough to technically be called La Nina. In other words, as temperature is going up, it's not coming down enough between the El Nino events to call it La Nina anymore. So they've invented a new term called La Nada, which I hate because it means the nothing, right? Which makes it sound like it's completely innocuous. But part of it is it's happening fast. It's a huge area. You can see the reef from space. So I doubt there's much you can do. Jeff.
So just hypothetical, what would be your recommendations if you could tell all the countries what to do? If you were the global warming czar.
So I honestly think we should, number one, we should stop the character assassination stuff. We should stop attacking people instead of their ideas. And I think that's on all sides, right? So it doesn't do anybody good to that person doesn't know what they're talking about because that person's not a real scientist or that kind of stuff. I don't think that's productive. I think the second thing maybe is to try to approach the person as though these are complicated things, and so it's not the case. I think where people are just the word my son uses, trolling us, right? Just trying to throw things out there because they're just trying to stir up trouble. I think people are genuinely confused, and it's hard, and there's a lot of facets to it. And when that happens, people throw their hands up. They have to rely on experts. The experts seem to conflict with each other, so what do? It's difficult. I think one of the things that has to happen that I'd like to see is to be clear about facts and data. And the example of the 97% is a good one. It is the first study that was done looked at, I think, 14,000 peer-reviewed articles and found a few that didn't either directly or some way imply anthropogenic change. It's since been done again and found 91%, 93%, 97%, 98% by 7 different studies. But when it gets into the media, it's 97% of scientists say the polar caps are melting. No, they don't. And the farther you get away from climate scientists, the number's going to go down because people don't have the expertise. I'm not in that 90. Nobody asked me my opinion, right? I'm not a climate scientist in the sense of putting those papers out. Our medical people, doctors, my brother's a scientist then. Does his opinion about climate change matter? So preciseness about language is, I think, important too. And trying to clear up misconceptions. So all of those things together.
On that topic of confusion, I had an opportunity to premiere our film Groundswell Rising. It's on a fracking movement in Paris during COP21, which was a very exhilarating experience for us. But there was no confusion there. The confusion is in America.
Yeah.
It's not an international confusion. It's here in America. And that's a great book, Merchants of Doubt. I mean, what's happening is that the fossil fuel companies are doing the same thing that the cigarette companies did. And they created doubt about whether cigarette smoking causes cancer. The same advertising firm is representing the fossil fuel companies, and that's why America is the only nation where this doubt exists.
Yeah.
It does not exist in other nations.
That's right.
By the way, this is excellent. This presentation you're doing is outstanding.
Thank you.
But I really want to call on the university to do the clean energy talk at another time. That the rest of the world is done with this discussion.
Right.
They're not having this discussion.
Right.
Their discussion is clean energy. That's what we need to talk about.
I agree. I think that would be a great talk to have. And to the point of places like the Heartland Institute, not only were the same institutes that are now putting out information about climate change, putting it back, the main source of funding to start that was R.J. Reynolds, and they were the main proponents of there's no link between secondhand smoke and cancer and all of that. Not only is it the same institutes, as I like to tell the students, it's some of the same scientists. So I always kind of thought before I looked into it, it was the same kind of scientist who would kind of look at the data and be in that 3% or something. It is often the same exact person that was an expert in tobacco and carcinogens and the effects of smoking, who then in the 90s became the expert in climate change and ozonation and the ozone hole. The same people. All right, so last part, quickly, is some of the research we've done here to try to look at some of these effects. I'm going to just touch on 3 quick areas and say that I'm happy to talk to anybody on campus at any time about any of this. And I mean that sincerely. I don't think there's anything more important in my career now to talk about. And so the door is open for whoever wants to have a chat, argument, debate, discussion. I don't care. I want to talk about this with people if they're interested. I'm in SciTech 225, if you're curious. We have the Chincoteague Bay Field Station in Wallops, Virginia. Marine science students go there to take summer classes. One of the projects that we're looking at happened at our lab at Greenbackville, Maryland. This picture was taken in 2011 after Hurricane Irene. We lost about, on average, 3 feet of shoreline, 8 feet in this picture, in one night after Hurricane Sandy came through. And so we decided we were going to try and turn this into a restoration project. The oyster beds that were there all got depleted out overnight. They all got kind of ripped up and put out in the middle of the bay. So we worked with the Nature Conservancy to get these oyster castles put in to try to help entice recruitment of oysters. And we started looking at the effects on erosion. And as you see, the oyster castles here, they're already working, because these sort of points of, you can see kind of where the beach sticks out pointing towards the castle a little bit. It's because as the waves crash, it breaks the energy, the sand settles behind them and helps prevent some of the erosion. Students who go down there are helping a long-term monitoring program here. I see Luke in the audience who came back. This is Luke in the picture from several years ago. And so they go out, they can look at the beach, the marsh, and the ocean, and they're helping to do this for their marine ecology class, but also I'm keeping the data as a long-term data set. This is not the kind of stuff you can go to Walmart and just buy, so students are also learning how to sort of be creative in making equipment that are going to be able to look at oyster settlement, barnacle settlement, the kinds of things that we're looking for and how it relates to sea level rise. Sea level rise is more of a problem in the mid-Atlantic than anywhere else in the continental US. People tend to think of sea level rise like getting in a bathtub. It's not. Sea level rise also, it can have relative sea level rise. As water goes up, land can subside, right? This is another thing with Greenland, is as the ice is melting, not only is there a gravity effect, but there's isostatic rebound. It's like when you get off your sofa cushion, the butt print kind of slowly rises back. Well, when the ice melts, the land kind of slowly comes back up as well. That's going to make it appear like sea level is dropping. So we're looking for animals and organisms that live between the sand grains. We're trying to get a baseline of what's there so we can start looking for how it might be changing. That project's been going on for 5 years. We've got students that are starting to present on it now, both as part of class, also at Pennsylvania Academy of Science, also at national meetings for estuary and coastal work. One of the other areas of research we're doing is looking at coral reefs off Roatan, Honduras. I've been taking a class there now for 11 years every summer. These are all ESU students that are doing some investigations, transecting, quadret work, all those sorts of things that you would expect to see. And so they're helping, again, generate a long-term data set on how much coral is there, how much cover is there, the types of coral that are there, the types of algae that are there, and trying to keep a long-term track of it. We decided a few years ago that conservation wasn't enough. We need to start looking at restoration. And so we're helping the director at this institute. She erected these things called coral trees. They're all little living coral fragments that are hanging away from the reef, away from the predation, away from the siltation, and they're allowed to grow out in the open ocean. And then students will come and take them, clean them like they're doing here, and eventually we're going to have them cement them back onto the reef to actually try to put corals back onto the reef. Additionally, I started working with Darlene Ferris-Lavar in the art department with her 3D printer to 3D print some different types of substrate, and we're looking for ways of trying to naturally, or at least looking naturally, cement some 3D printed objects that would help to recruit coral larvae and be easier to cement them on. So we're trying to actually restore the reef instead of just conserve it. And finally, this August, I had a chance to join some colleagues from GEMSTEC with, where is she? Leah Bergman, as ESU undergrad student. We flew out to Dutch Harbor. The idea was here that we know the Arctic is changing rapidly. It's warming roughly 4 times as fast as the global average. We don't know as much about the subarctic, and so we went out there to look for the gelatinous organisms and such to try to get a baseline for what's going on there. So we met the research vessel, and there was all kinds of wonderful equipment there to gather video and photographs, plankton, water samples, sediment samples, and all of this stuff is going to be analyzed. We came home with, I think it was 3 terabytes of raw data, and I estimate it's going to take at least 12 to 18 months to go through all of that. I put this picture in here just to remind me what it's like to be on a Japanese ship. This is the storage room for the science equipment. I don't know, that just blows me away because usually the storage room is the lab, and people are playing like Rubik's Lab to try to move boxes around. Those crates are each 2 meters by 2 meters by 2 meters, and they had room left over. They hadn't even filled yet. Operations were 24 hours a day, day and night. Leah will tell you, it was 3 weeks. It felt like 3 months because you slept for 2 hours, you got up, you slept for 2 hours, you got up, and you did that round the clock because that's when the data was coming up. She did a good job. She worked very hard. We brought the animals in the lab. We were able to sample some, get some pictures, get some video, process some of the samples, and bring them back to ESU. I'm really interested in the calcification of the animals and looking at some of them. Leah was interested in the fish. She's measuring some of the deep sea fish and has brought them back to study them. But one of the most fantastic parts of this, we went to this area because there's a biodiversity hotspot there where occasionally, for reasons that aren't clear yet, phytoplankton blooms, which brings in krill, little shrimp-like animals, which brings in cod fish, which brings in whales and birds by the tens of thousands, shearwaters. We actually thought the chance of seeing this was probably less than 50%. Just because it's rare, we don't know where it's going to happen. We saw it on the first day we were out, or the first full day we were out, and got really lucky. We had, I'm going to estimate on any given day, 100 to 200 humpback whales coming in and feeding, The birds is an open question. Some of us are saying tens of thousands, some are saying hundreds of thousands. More birds than I've ever seen in my entire life. I've been going to sea for almost 30 years. I added it up once. I've actually spent 1.5 years of my life at sea. I've seen something like this twice. This is the second time. The first time was a big school of bonito that I couldn't even see the horizon. It was so big. But it was a terrific experience to see. The birds would come in, the whales would stir up some of the plankton, and they would feed. We had a film crew there. They did a documentary. It's actually going to air this Friday night in Japan, though, TV Asahi, if you want to live stream it. But it was just a terrific trip. We actually got to see, the Japanese call this Aleutian magic because of the biodiversity hotspot. We actually got to see it three or four times. There's one time we saw it was really fantastic in birds as far as the eye can see, but you see some of the whale spouts in the middle and the tails as they're doing their feeding. So that was tremendously exciting to do, and now we're trying to put together, we took a lot of, because we hit it early, we were able to actually change the entire dive plan to go looking for the physical chemistry of the water to show what's happening different that got the plankton there in the first place. So we feel like we hit it lucky, and we're trying to work on exactly what's going on in the water that leads to the plankton being there, that leads to the whales and the fish and the birds all being there. Now, you notice I didn't show you a polar bear starving on an ice floe. I didn't go to any of that kind of stuff, although I probably could have. But there is one thing I want to show you, because we talk a lot about generalizations. The room is warm. People are sleepy. I'm not trying to depress anybody, but there are hundreds every year of example of how our changing the climate is having an impact on life, including human life. We shouldn't forget. The one I'm going to show you is this guy. Aw. These are Adelie penguins. Adelie penguins, like many marine birds, the parents usually just raise one chick, sometimes two, but they have to feed these chicks with food. They have to grow fast. They have to get in the ocean, which, as we already said, sucks the heat right out of you. So there's a lot of energy that has to go in parenting a chick. Adelie penguins this year, in 2017, 40,000 of them hatched. Number of survivors, 2. Not 2%, not 2,000, 2. That is 2 more than survived in 2013. So we could talk about examples like that till I'm blue in the face and just depress you. And we all go out for a beer, and then that's what we do. But I don't think we have to start there. I think we can start with just the data and the facts and have a reasonable conversation to kind of move this forward. And I've forgotten your name, and I apologize greatly for that. I'm sorry, what was your name?
I'm Mark.
Mark, I forgot. I'm sorry, Mark. Mark actually came to a class. He went to COP 21, gave some terrific information on some of this, and I think he makes a really terrific point, which is this really isn't controversial in most of the rest of the world. It isn't. And so we need to have that conversation about what's real and what's not. And I'm not going to talk about the Apple banana commercial. But the first time I saw the Apple banana commercial, I thought, are we in this state now where CNN has to put on a commercial that says this is an apple? If you don't know what I'm talking about, look it up. All right, that's all I have. I'll stay around if people have questions. Thank you so much.